All right, welcome to The Explainer. Today, we're diving into something really cool, modeling and simulation. We're going to talk about how we can build these simplified digital worlds to get a better handle on and even predict our own very complex reality. And to kick things off, I've got a puzzle for you that sounds just about impossible. But trust me, stick around, because by the end of this, you are going to see exactly how a little bit of structured chaos can solve it. So, here's our game plan. We're going to start with the basics. What even is a model? Then, we'll see how to bring one to life in a simulation. After that, we'll explore how randomness can actually be a super powerful tool. And we'll wrap it all up by applying this to a problem we all know: waiting in line.
Okay, first things first. To understand anything complicated, doesn't matter if it's the global economy or just your local coffee shop, you first need a simplified version of it. And that simplified version, well, that's what we call a model.
The best way to think about a model is like a city map. It's not the city itself, right? It doesn't have all the noise and the people and the smells, but it gives you all the essential stuff: the streets, the landmarks, everything you need to get from point A to point B. It's basically a blueprint of reality.
Now, models come in a couple of different flavors. You've got your static model, which is like a photograph. It's a fixed snapshot in time, kind of like a floor plan for a room. Then you have the dynamic model, which is more like a movie. It evolves, it changes over time, just like your bank account balance does from one month to the next.
Models can also be deterministic. That just means if you put the same info in, you get the exact same results out every single time. Think of a simple formula like distance equals speed times time. Or they can be probabilistic, and these are the fun ones. They embrace chance, they have multiple possible outcomes, kind of like rolling a pair of dice.
And there are a few different ways we can actually build these models. We can make physical, tangible versions, like a globe or an architect's model of a building. We could draw them out visually, like in a flowchart, to map out a process. Or, if we want ultimate precision, we can describe them using the pure logic of mathematics.
But no matter what kind of model it is, building a good one always comes down to these three key steps. First, know why you're building it. What's the question you're trying to answer? Second, figure out all the crucial components. And finally, choose the best way to actually represent them.
So once we have our blueprint, our model, we need a place to actually bring it to life and test it out. And that's where simulation comes in. You can think of it as our digital sandbox.
A simulation is basically the act of making a model run. We get to play with it, tweak the variables, and run it over and over again just to see what happens. It lets us predict outcomes without having to run messy, expensive experiments in the real world.
Let's take a super common mathematical model: compound interest. We can simulate this really easily, even in a basic spreadsheet. So let's say we start with yen. At a 3% interest rate, our simulation just plays out the model over time, and we can literally watch that balance grow year after year.
And the logic that's powering this whole dynamic model? It's incredibly simple. It's just that the money you have at the end of this year becomes the new starting point for calculating the interest you're going to earn next year.
And if you peek behind the curtain, here's how the simulation actually works. It's just a set of simple, repeated rules. Each new balance is just the old balance plus the new interest. This simple, repetitive logic is what lets the model play out and show us the future.
Okay, so we've seen how to simulate a nice, predictable system like interest rates. But let's be real, the world is messy. It's unpredictable. What happens if our model needs a dose of randomness? Well, it turns out we can actually use that randomness to find some surprisingly precise answers.
It's this really powerful technique called the Monte Carlo method. Basically, it's a way of solving problems by running a simulation thousands or even millions of times with random inputs and then just looking at the overall results. It's kind of like finding an answer by playing a game of chance over and over and over again.
All right, let's get back to that puzzle from the beginning. How do we find pi? Well, first, our simulation generates thousands of random points inside a perfect square. Step 2. For every single one of those points, it checks if it also landed inside a circle that's drawn perfectly within that square. And finally, it looks at the ratio of points inside the circle to the total number of points it generated.
And here is the magic. You see, the ratio of the circle's area to the square's area just happens to be pi divided by 4. So if we're just throwing points randomly, the ratio of points inside the circle to the total points should also be about pi over 4. We are using probability to measure area. So we just multiply that ratio by 4, and boom, you get a shockingly good approximation of pi.
And here's a little peek at what the simulation is actually doing under the hood. For each point, It just generates a random x and y coordinate. Then, with a little bit of simple math, it figures out if that point is inside or outside the circle's boundary, and it assigns a 1 if it's in and a 0 if it's out.
And this is the crucial part. The more random points we throw at our model, the more accurate our answer gets. I mean, with just a few hundred points, the result might be a little off. But with millions of points, our simulated value gets incredibly close to the actual value of pi.
So this isn't just for, calculating abstract math constants. We can use these exact same ideas, modeling and simulation, to analyze something we are all experts in: waiting in a line.
When you break it down, a queue is really just a model for a waiting line. And we can define this whole system with just a few key variables: how often people show up, how long it takes to actually help them, and the result of those two things, which is how long they have to wait. Okay, let's simulate a simple supermarket checkout. Customer 1 walks up, gets served right away. Great! But they take 40 minutes. So when customer 2 arrives at the 20-minute mark, they have to wait another 20 minutes before their service can even start. And you can see right there how the wait times just cascade and get longer for every person who comes after.
And just like that, our simple little model gives us some really powerful insights. We can see exactly how long each person's service takes, we know who had the longest wait, and we can even pinpoint the exact time window when the line was at its absolute worst. I mean, this is data a store manager could actually use to figure out when to open a second register.
And that's really the power of this whole process, isn't it? We started with a simple blueprint, a model. We brought it to life in a digital sandbox, a simulation. We even saw how to use total randomness to find pi, and then applied that exact same thinking to a supermarket line. It's a tool that gives us a lens to not just understand our complicated world, but to predict it, test it, and maybe, just maybe, to improve it. So that leaves one question: what complex problem should we model next?